This is one of my favorite images taken of all time. It's the surface of 67P Churyumov-Gerasimenko, a comet just a few kilometers across, and it was taken by the European Space Agency's Rosetta spacecraft. Launched in 2004, the spacecraft reached the comet in 2014 and spent 2 years orbiting the tiny, icy world before landing on its surface. To me, the most striking thing about this image is how familiar it is. If you take away the cosmic rays, those little straight lines that flash in and out, you could almost mistake this for a snowy mountaintop on Earth. To me, it shows just how much we have in common with even the most exotic places in the solar system. To get this image, the European Space Agency had to combine several clever bits of technology. They had to launch the spacecraft with precision timing. They had to get it to survive on its multi-year journey through the vastness of the solar system. They had to get the spacecraft to intercept a comet traveling at tens of thousands of kilometers per hour, enter into an orbit around it, deploy solar panels for electricity, deploy all its scientific instruments, collect data, send that data back to Earth, and then land on an object so small it barely has any gravitational attraction to speak of. That mission was over a decade ago. And we have much more ambitious plans in the works. We don't want to just land on comets, we want to dig into them. We want to explore the potential riches of the asteroids. We want to send rovers hunting for signs of life on Mars. We want to send flying craft to the worlds of the outer solar system. We want to build the foundations of a permanent presence on the moon. But we know that we can't have all that right now because it's hard and expensive. We vaguely understand that we need to improve our technology if we want to have a more permanent presence in deep space. But what exactly do we need to improve and when? What should we be working on right now to make the tomorrow that we dream of possible? NASA's got a plan. Well, it's more like a concept of a plan, but it's a start. NASA's been working on a lot of cool space technologies for decades, like extravehicular suits and rovers and food that isn't disgusting. But a lot of that technology development has been undirected, with groups or researchers here and there deciding what they want to work on, or a mission gets spun up and everyone just sits down to figure out how to make that one mission happen. This year, NASA decided that this process wasn't working out very well, since they couldn't always line up their needs to what people were working on. So they shook things up a bit. Instead of focusing on one particular mission or just letting random people fire off ideas, they tasked themselves with coming up with a comprehensive list of fundamental technologies or categories of technologies that could enable a wide variety of long-term operations in deep space, whether that meant a permanent human presence on the moon or fleets of autonomous vehicles exploring the outer solar system. To make this list of shortfalls, as they called them, NASA worked with their own people as well as partners in industry and universities. And what a list it is, containing 187 individual shortfalls, each one describing a key technology that we need to develop or improve upon to enable the next generation of space activities. Now, obviously, we can't work on all 187 items at once, at least with current budgets, so the next step was to prioritize them, with NASA asking all their partners to rank them. The end result of this enormous process is the Civil Space Shortfall Ranking, which is basically NASA's Christmas wish list. Now, I won't go through all 187 shortfalls, unless you want me to, so today we'll stick it to the top 5 ranked technologies that NASA believes we need to develop if we want to go to space and stay there.
You just made the list!
Wrestling with complex questions requires understanding many subjects at once, which is why I'm thrilled that this episode is sponsored by Brilliant. If you like learning new things, and I know you do because why else would you be here, then Brilliant is a great place to spend some extra time. Brilliant is where you learn by doing, with thousands of interactive lessons in math, data analysis, programming, and AI. Brilliant is a learning platform designed to be effective. Don't think classroom lectures. Think hands-on problem solving that builds from first principles and goes from there. One course I especially like is on calculus. I know that calculus can be intimidating, but it's the foundational tool set for, among many other things, understanding how things change. Brilliant's course walks you through the basic steps of calculus, allowing you to build up the skills necessary to master this branch of mathematics. To try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/Paul Sutter or scan the QR code on screen, or you can click on the link in the description. You'll also get 20% off an annual premium subscription. And we'll start with number 5, high-powered robotics. Space is hard. There's no doubt about that. It's completely unlike any environment we have ever faced on the Earth. Explorers in space, whether human or robotic, have to tackle literally out-of-this-world challenges. For example, there are extreme temperature fluctuations. One minute, it could be hot enough to boil water, and the next minute, cold enough to freeze nitrogen. Without thick atmospheres to balance and distribute heat, within the inner solar system, you're at the mercy of the sun. If you're in sunlight, it's generally going to be too warm. And if you're in the shade, it's hundreds of degrees colder.
That's all you gotta say, scariest environment imaginable.
In the outer solar system, it's just cold. Always miserably cold. And then there's the dust. On the Earth, dust is irritating. It can make us sneeze, and it can jam up gears or wheels or cause your brakes to make that loud "gwee" sound. But in space, dust is next level. The surface of the moon is covered in a fine powder called regolith that is both tiny and microscopically full of jagged edges. This dust can worm itself through even our best sealed compartments, or just get carried along for the ride where it immediately sticks to everything. And hey, who doesn't love a dose of deadly radiation every single second of every single day? Without a protective magnetic field and the security blanket of a nice thick atmosphere, operations on the moon and Mars require constant exposure to cosmic rays, which are tiny charged particles slamming through the universe. Cosmic rays are caused by super energetic events in the universe like supernova and active galactic nuclei. And a typical cosmic ray particle is traveling somewhere around 99.9999999% the speed of light. That's a lot of nines and a lot of trouble. These cosmic rays can fry electronics and snip apart DNA. And yeah, we've been sending robots into this extreme environment for decades. But if we want a more permanent presence on the moon and Mars, we have to do better. For sure, we've had some huge successes, like the Cassini mission that spent 13 years in orbit around Saturn, or the Mars exploration rovers Spirit and Opportunity, which lasted years longer than their planned 90-day missions. Those missions produced an enormous amount of science results, like the fact that we now have firm evidence that liquid water once existed on the Martian surface. We have been able to gather this evidence with the instruments on our rovers, like rock abrasion tools and alpha particle X-ray spectrometers, in addition to good old-fashioned cameras. But the presence of liquid water in the Martian past has opened up a powerful, difficult question. Did Mars once harbor life? Unfortunately, our current suite of robotic instruments are too limited to tell us. We need to be able to dig deeper into the soil, survey more regions, and bring more powerful instruments to answer that burning question. This isn't just limited to Mars rovers. In general, every robot we send into space has a limited lifespan. They're not meant to be repaired, and they're extremely limited in what they can do. And still, those missions cost hundreds of millions, if not billions of dollars, because we're trying to battle all of those hostile environmental factors. On the Earth, we've made great strides in making larger and more powerful robots. We have heavy-duty robots that can assemble cars, and we have versatile ones that can walk like humans. To make more impressive robots, designers have focused on increasing the power density. This is the amount of energy that robots can store and send through their various parts and systems. These systems include sensing, actuation, which is moving various bits and parts around, and aviation like flight control. The more power you have available to all those systems, the more you can do. But if we rank power density on a scale, like a wind-up toy being a 1 and a kaiju-killing Jaeger a 10, our robotic space probes are like a 2, maybe a 3 if we're being generous. It's not just about having a big battery pack or a huge solar cell. We need the ability to get this power to a robot's subsystems. We need more powerful electric motors, gearing, and drivetrain components. We need more capable sensors with more dynamic range, more perception, and more force. We need long-lived power distribution systems, like cables and wires. We need more powerful computers to drive all of this. And if this weren't enough, we need future robots to be modular so that we can easily swap out components to allow the robot to fulfill a new mission objective. And we need our robots to be repairable and maintainable because we simply can't build up a healthy lunar or Martian infrastructure with single-shot spacecraft. In fact, we probably need space-based robots that are even more capable and more power-dense than their current terrestrial cousins. This means that our goal isn't just to make current top-of-the-line Earth robots capable of facing the dangers and challenges of space environments. No, we need even better. Next, we have number 4, improved navigation. We all take for granted our handy little cell phones, those magical rectangles that let us communicate instantly with anyone in the world, or scroll social media until our brains go numb. Related to that is the ease of navigation. You can plug in an address or drop a pin and boom, there you go, the fastest route to grandma's house. Oh yeah, and you always know what time it is, day or night or season of the year, so you always know that you're late for dinner. All of this is easy for us to use because it was hard for someone else to create. To make a call, our cell phone connects to a nearby tower, of which there are approximately a bajillion, which is then connected to a vast globe-spanning network of wires and undersea cables. As for our position and navigation, that's all handled by hundreds of satellites in orbit around the Earth. There are several different networks here. There's the United States Global Position System, the OG, Russia's Global Navigation Satellite System, China's Beidou, and the European Union's Galileo. We have all that, plus a host of regional and local space and ground-based location services, all overlapping and working together to provide that pinpoint accuracy. But in space, like on the Moon or Mars, we have none of that. Zero. No GPS satellites, no globe-spanning networks, just radio broadcasts from command centers here on Earth telling our robots and crews what to do. And so we have the next high-priority challenge we have to navigate, that's a clever pun, to achieve a permanent presence in space. All that stuff, but in space. So what would this look like? The most important step is to create a mini GPS for the Moon, with a constellation of satellites doing for the Moon what they already do for the Earth. Plus, we need to augment that with relay stations and repeaters at lunar bases or centers of exploration, because we probably won't have enough signal strength to whip out our cell phones in the middle of Mare Vaporum. The hope is that our first generation of lunar GPS will be enough to match our first explorations, and then we can expand the system to match the needs of further lunar activities. But in order to make that lunar GPS system, we need to deploy in space one critical piece of technology: atomic clocks. Atomic clocks are ultra-precise, clocks that rely on the resonant frequency of atoms to monitor the passage of time. We already have atomic clocks in space because every single GPS satellite has several of them on board. That's the key component to the entire navigation system. But for deep space work, we need to be much more sophisticated. Earth-based atomic clocks can get away with some uncertainty because they are always cross-checking and correcting each other. That won't be an option around the Moon or Mars, where a small network of satellites will have to keep perfect time. Precision timing is necessary for pinpointing a satellite's location. If you receive a signal from the satellite to a ground station, you need to know how long it took for you to receive the signal to figure out where the satellite is. In June of 2019, NASA launched the Deep Space Atomic Clock, or DSAC, which operated for 2 years, maintaining an accuracy of better than 1 nanosecond in 10 days. That means after 10 years, the clock would only be off by a microsecond. NASA has recognized that to enable long-term deep space activities, we need to be even more accurate than that. Lunar and Martian spacecraft are going to have to be able to navigate autonomously without human input. As a complement to a space-based GPS system, these spacecraft could also employ a few other tricks. One trick is called radiometric tracking, which uses incoming radio signals to judge the distance to the source of those radio signals. We already use this technique quite frequently, but it's limited to one dimension: the direction towards the Earth, which is the origin of any radio signal that a spacecraft might pick up. Decades from now, we hope to have radio signals coming from lunar and Martian bases and even asteroids, and a sufficiently sophisticated spacecraft might be able to pick up all these signals and figure out where it is in the solar system. Speaking of weak radio signals, lunar operations might benefit from our existing GPS network. Yes, those GPS satellites are aiming their signals down to the Earth, but some of that signal leaks out into outer space. We might be able to piggyback off that signal to at least get our navigation game started. That brings us to the number 3 highest priority technology for long-term space activities: better computers. Computers have been involved in spaceflight since almost the very beginning. Just like on the Earth, computers aid in a variety of tasks like navigation and communication. But unfortunately, space is really unkind to electronics. It's not so much the vacuum of space; a circuit board does just fine. And freezing cold temperatures aren't that big of an issue either. No, it's our old friends, the cosmic rays. Each cosmic ray consists of a single proton or atomic nucleus, and the most powerful ones have the energy equivalent to a thrown baseball, which doesn't sound like much, but when you cram that baseball down to the size of a subatomic particle, it can be pretty nasty. Most cosmic rays slip through tissues and computer circuitry with ease. They're so small, they literally miss the atoms and molecules of larger objects. But every once in a while they can strike, delivering all their energy to whatever they encounter. In humans, this can lead to an increased risk of cancer. In computers, it can lead to fatal glitches. Check this out. In 2022, the Voyager 1 spacecraft, which was launched all the way back in 1977 and is currently sailing beyond the borders of the solar system, started sending back garbled transmissions. By this point, Voyager had spent decades cruising the outer solar system, giving us the most pristine images of the giant planets and our first taste of interstellar space. Most of the spacecraft was operating normally, but not the attitude, articulation, and control system, which is responsible for keeping Voyager's radio antenna pointed back to Earth. It was just creating nonsense. Engineers were able to fix the issue by uploading the equivalent of a software update to route around the malfunctioning circuitry, although they never discovered the root cause of the problem. Many suspect that a cosmic ray struck a piece of circuitry at just the wrong moment to cause the problem. More sophisticated computers are vulnerable as well. In 2023, the James Webb Space Telescope, the largest and most advanced telescope ever sent into space, suffered a minor malfunction when its near-infrared imager and slitless spectrograph, or NIRISS, an important scientific instrument used to study exoplanets, became unsynchronized with the rest of the spacecraft, rendering it useless. NASA engineers suspected a cosmic ray led to the malfunction, but thankfully they were able to restore order by essentially turning it off and turning it back on again. These issues were easy to solve, but it's only a matter of time before a cosmic ray strikes at a critical moment, shutting down a much more important mission. To protect against the ever-present threat of cosmic rays, spacecraft engineers take years to develop onboard computers and ensure that they are hardened against radiation. It's for this reason that computers going into space tend to be a couple or more generations behind the curve. In 1969, the Apollo 11 mission's guidance computer weighed 70 pounds and was capable of performing about 40,000 instructions per second, which seems impressive, but that's over 100,000 times slower than the smartphone you're watching this show on. The International Space Station featured several custom-built computers, which took nearly a decade to develop. If we're going to maintain a larger presence in space, this isn't going to cut it. We need advanced hardware to handle a variety of complex tasks, like more sophisticated navigation and tracking, much larger data communication loads, assistance with scientific surveys and studies, and more. Plus, we need our computers to be more fault-tolerant so that a stray cosmic ray doesn't derail an entire mission. And we need to be able to easily swap out computing modules when they go space crazy on us, because we need maximum adaptability to achieve our long-term plans. Ironically, one of our biggest challenges with sending more powerful computers into space is how to deal with the heat. Yes, away from the sun, space is cold, just a few degrees above absolute zero. But it's also a vacuum, which means there is no air or water to easily transport away heat. It's not like you can just plop a fan on the side of the CPU. Heat can easily build up to dangerous levels, or at least dangerous when it comes to delicate circuitry. Plus, shielding against cosmic rays isn't as simple as just putting up a wall. That's because cosmic rays can strike the molecules in the wall itself and send out a shower of still energetic particles that can disrupt circuitry. We'll have to come up with many clever solutions if we want our space-based computers to be as fast and reliable as our Earthbound ones. Coming in second place is nothing less than more power. Which is kind of obvious. We want bigger and faster computers, we want more powerful robotics, and we want more sophisticated navigation systems. All that is going to take a lot of juice. What we have right now just doesn't cut it. Right now, if you want power in space, you essentially have two options: solar panels and a kind of nuclear power called radioisotope thermoelectric generators. Solar panels are exactly what you think of because it's very similar to what we have on the Earth. On the plus side, solar panels are relatively cheap to make and deploy and contain no moving parts, which is always a bonus when it comes to space applications. However, there are major downsides. One, anything outside the Earth's orbit is going to be tight on energy relying on solar panels because there's not a lot of sunlight. Also, there's no sun in the shade. Which I know is an incredibly obvious statement to make, but matters if you're, say, on the moon and get plunged into darkness for 2 weeks at a time. Even the International Space Station, which receives the same amount of sunlight as the Earth, because it's in Earth's orbit, has over 262,000 individual solar cells spanning over an acre, which is over 2,500 square meters for you metric folks. And all that generates, on average, an impressive 84 to 120 kilowatts of electricity, which could power a handful of typical homes. NASA's Juno spacecraft currently holds the record for the most distant deployed solar panels in the system, orbiting around Jupiter at a distance of over 800 million kilometers. Its gigantic solar array could generate 14,000 watts of power on the Earth, but at that distance, sunlight is so feeble, it only manages a measly 500 watts of power, which could run a kitchen blender. You know, if you needed to make a smoothie on Jupiter. But Juno was able to turn that juice into the most detailed images ever taken of the storms and cloud tops of the giant planet. And it used slight variations in gravity and magnetic fields to give us a sense of what's happening deep beneath the surface. The alternative for deep space missions is the RTG, or radioisotope thermoelectric generator. This device is essentially a chunk of radioactive material that decays. As it does, it releases heat, which can be used to generate electricity. It's basically like a nuclear battery. On the upside, these things last basically forever, giving spacecraft decades of reliable power. But on the downside, they don't deliver a lot of power, and they slowly lose power over time. And there's the whole nuclear thing, which makes some people a little twitchy. But here's the thing. If we're going to stay in space for the long haul, we have to get over that whole nuclear thing real quick. And that doesn't mean more RTGs. That means full-on nuclear power plants on lunar and Martian bases. Yeah, you heard me right. Look, it's not like we don't know how to make relatively compact nuclear power plants. Submarines and aircraft carriers around the world all carry their own little power plants. But those things are beyond heavy, which make them impractical to launch in a single mission. And nobody really likes the idea of trying to assemble one in Earth orbit. So we have to get clever. We're going to have to figure out how to make a smaller, launchable fission power plant. And the most difficult challenge, honestly, will be convincing the public that we can launch nuclear material into space and totally not have it blow up in the atmosphere we promise. I mean, it's kind of a legit concern. It's not like we'll have a nuclear bomb going off or anything, but also nobody wants some rocket blowing up and having it rain radioactive material across a sizable fraction of a continent. It's not likely to happen, but there is the possibility. And NASA and its partners will have its work cut out to convince the public that it's a small enough risk and a great enough reward. In the meantime, while we're figuring out all the bits and pieces that will make safe, efficient nuclear power in space a viable option, we have to up our game with solar panels. That's really the only other power source we can rely on. It's not like there are coal or oil deposits on the moon or Mars, so we need more efficient solar panels, lighter solar panels, and the ability to deploy solar farms in sunlit areas and transmit that generated power to our bases and stations. Those solar panels are going to have to be more durable than current ones, as they have to deal with micrometeorite impacts and the destruction caused by the sun's unfiltered UV radiation. Oh, and don't forget the dust. The always present, always persistent, always annoying dust that just gets everywhere. The only reason that the Spirit and Opportunity rovers were able to go past their planned mission lifetimes was that random Martian dust devils would wipe away the dust off their solar panels. And we can't rely on dust devils as a long-term solution. And finally, after multiple rounds of voting from NASA centers, industry partners, and academic researchers, the highest priority goal we need to accomplish to make all of our space dreams come true is surviving the lunar night. Now, I know this sounds like a low-budget knockoff of Five Nights at Freddy's, but it's the real deal. The lunar night is no fun at all. For one, it typically lasts 2 weeks at a time, although there are some peaks that receive sunlight almost permanently, but on the other hand, there are also regions where sun never strikes at all. For another, temperatures can plummet down to 35 degrees above absolute zero. This is absolutely unprecedented. There is no analogy to anything we have experienced on the Earth. Even in Arctic regions, where the sun can disappear for months at a time, are helped by the fact that we can still have an atmosphere that can retain and distribute heat. When the sun shines on the equator, some of that heat makes it to the poles, but the moon has no atmosphere, and so the only heat you get is from the sun. When it's gone, it's gone. This makes nighttime operations a serious challenge. It's really hard to design electronics, and especially batteries, that can function for long periods of time at low temperatures, because almost all of our battery designs rely on chemical processes to generate electricity, processes that slow down at low temperatures. And all of our electronics are designed to work, on Earth. There has been some headway in the direction of surviving the lunar night. In early 2024, the Japanese lander SLIM, for Smart Lander for Investigating Moon, also known by the much cooler anime nickname of Moon Sniper, made history by surviving 3 lunar nights. That's 3 4-week cycles of light and darkness. But to survive the nights, the lander had to shut down and enter a hibernation state, hoping that its batteries would stay warm enough to power itself back up once daylight hit again. So while that technically counts as surviving the lunar night, that's not exactly what NASA and its partners had in mind when they ranked this as their #1 challenge. We can't just go into a low-power sleep mode every 2 weeks, especially if we're talking about extended human or even robotic activities on the lunar surface. Surviving the lunar night means transitioning from a daylight temperature of over a blistering 120 degrees Celsius or 260 degrees Fahrenheit, all the way down to negative 240 Celsius at night, which is negative a lot in Fahrenheit. On the other side of the coin, our own robotics and electronics are going to generate their own heat anywhere from 5 to 10,000 watts. We need to efficiently manage that heat and make sure it doesn't warp or destroy other vital components on its way out of the spacecraft, especially when the outside temperatures will vary so much. What will it take to enable lunar night operations? Well, we need components that can manage those kinds of massive temperature swings and still operate efficiently in frigid conditions. We need systems that can efficiently dump heat in both freezing and boiling outside conditions. We need large solar panels that can absorb energy during the daytime and low-temperature batteries that can continue to supply that power through the night. We can't just have those components specialized to one temperature extreme or the other. They need to be able to handle both. I see this challenge as the culmination of all the other ones. Surviving the lunar night isn't easy, but it serves as a critical milestone in our advance into space. If we want to survive the lunar night and maintain activities and exploration for those 2 weeks of darkness, we need to solve the other 4 challenges. This will be our true test. We can't just content ourselves with literal day trips or low-power night modes. We have to be able to maintain the same level of activity regardless of the daylight conditions. We need high-powered, capable robotics. We need reliable systems for timing and navigation. We need more sophisticated computers, and most importantly, we need a lot of electricity. If we can maintain robotic or crewed activities through lunar night after night, then we will have the technological base we need to create a more robust presence on the moon and extend even further into the solar system. It won't be easy. The lunar night is unforgivably cold, depressingly dark, and depressingly long. But hey, at least we'll get a good view of the stars. So what do you think? Do you think these priorities make sense, or do we need to go in a different direction? Let me know what you think in the comments, and thank you for sharing your time and space with me today.